Okay, hi. All right, now we're on to CCNA2, or second half of CCNT. So chapter 1 is routing concepts. So we're going to look at initial router configuration, and so how we do that. We'll look at how a router makes forwarding decisions for data packets, and we're going to look at how routers operate in general. Okay, so router configure functions. So basically, networks are relied on for web applications, IP telephony, video conferencing, interactive gaming, e-commerce, and much more. Characteristics referred to when discussing networks are topology, and so the topology is the design, and so there's the physical topology, and so that's where the physical devices are, and so it's about cables and devices and computers and or hosts, all those kinds of things, and so and how they connected together using wires, cables, or whatever. Logical topology is more about how things are organized, and so who is directly connected to who and what. Now, of course, when it comes to a network, I suppose the faster the better normally, but of course, the faster is normally the more expensive, and so you buy the speed you need and you can afford. Then there's cost. So again, as I said, the faster, the more expensive typically. So you know they're basically competing requirements basically. And so of course security is another thing that's a hot topic these days. And so original IP networks were not designed with security in mind at all. It's been an add-on later, but of course designing a network with security from the start does make it a bit better. So availability basically is how much time is it available for use, and so the more the better, I suppose. Scalability means basically can this network grow without groaning? So can it grow and then still handle the traffic? And then reliability is, basically, do you have single points of failure? So if a switch dies, will everyone be gone, or will just a small amount of people be affected, or and so on and so forth? And so, as well as purchasing equipment that is more reliable with its own components have got redundancy and things like that. And other things like mean time between failures for the devices you buy. So it's all things you can research. So why routing? So of course a router is used to connect one network to another. It determines the best route to the destination before forwarding traffic to the next router along the path. It's responsible for routing traffic between networks, and the routing table is used to make those, to determine the best route for the packet to get to its destination. So a router is basically a specialized computer. They've got a CPU, they've got an operating system, they've got permanent storage, they've got volatile storage, all the same things as the computer you sit down and type documents in. Some might be a little different. So of course, if you look in the specifics, the operating system for a Cisco router is iOS, Internet Network Operating System. And no, Apple didn't think of iOS first. When it comes to storage, well, RAM, pretty much the same. But of course, not many routers have a hard drive. They normally use flash as their non-volatile storage. And a ROM, read-only memory, well, pretty similar to at least how older computers worked. And of course, the other major difference between routers and other computers is they will often have specialized ports for connecting networks together. And of course, they're going to have more than one network port. Otherwise, there's not much point to the router. So having a look at, as we said, the storage here, RAM, exactly the same as a computer. It's volatile. That's where you put the operating system where it's running. This configuration ends up there. All of your working data ends up there as well. So like the routing table, ARP tables, packets can be stored there, the whole lot. So they're all, that's pretty much the same purpose as your computer. ROM, well, it's basically how the computer boots up. It will go to ROM first, and then ROM will do a post or power on self test, the diagnostic, make sure everything it needs is there, and then it will actually hunt for a full operating system. With routers, you actually do have a very basic iOS built into ROM, and so they can talk on a network. They won't be a router with just ROM, but they will be a host, and you can actually then connect to other devices and maybe transfer a full operating system if it's been destroyed somehow or other. Now, when it comes to non-volatile storage, while on a computer we have a hard drive or a solid state drive or whatever it might be, with routers they have two types. So there's flash, that's where you store the operating system. You can store other files as well, but storing files is not really a router's job. The most common files you might store is if you're doing intrusion prevention, you'd have your signature files stored in flash as well. When it comes to the configuration, that's actually stored in what's called NVRAM or non-volatile random access memory. It's basically flash anyway, but they've just given it a different name because it's organized separately. Okay, when it comes to physically looking at a router, this is a 1941, like what's in the rack on level 3. You have USB ports, so you can actually plug that in, transfer files to and from, and away you roll. We have network ports, and so there's G00 and G01. You have a console port, which I think we've discussed before. That's how you do your initial configuration. You can also use USB on these ones as well as a console port. They've both got that light blue code. Auxiliary port is designed to plug a modem into, and so you can actually do a little more remote administration with that. And then here, basically, we have the HWIC slots, so high-speed WAN interface card slots. And so, of course, in our rack, we've actually got serial cards in there, but, you can put in DSL ports or whatever is required, typically for your WAN connection. Okay, now, of course, routers, as we said, interconnect networks. And so because they interconnect more than one network, that's why they do the forwarding of packets between them. Multiple networks on a router require multiple interfaces that each belong to that different IP network. And so the Ethernet interfaces need to be configured to be on the LANs they need to be, and the WAN ports, of course, probably hook into your ISP or whoever it might be. When a packet arrives on a router's interface, the router might be the final destination, or we might have to send it to another router to reach its final destination. Okay, so routers choose the best paths, and so they use a routing table to do that. And so routers use the routing table like a map to discover the best path to a given network. And so the primary function of a router is to determine the best path to send packets, forward packets towards their destination. When a router receives a packet, examines the destination address of the packet and uses the routing table to look for the best path to that network. When a match is found, the router encapsulates the packet into the data link frame for the outgoing interface, and then forwards the packet out that interface towards its destination. A router can handle different data link layer frame encapsulations. As you can see on the router here, you've got an Ethernet LAN here, and you've got a serial port there. That would be either HDLC or PPP typically, and this would be Ethernet. Two different layer 2 encapsulations, and so you would actually strip the layer 2 off of it if it arrives from the Ethernet, and then put a different layer 2 on it to send it over the serial. Okay, now, of course, they make forwarding decisions, and then it's actually switching that is how it gets forwarded. So the decision is, where do I send it? The switching is sending it. So basically, there's more than one way to forward packets, and so there's process switching, which basically is what this first one is here. It arrives in an interface, and then it actually goes up through the CPU, through RAM, the whole lot, to be processed, and then makes a decision. Now, and so doing that is a slow way to do things. But what you can do is, if you've got fast switching as an option, the first packet will always go through this process, but it can actually update special registers so that, well, that's the first packet of a conversation. And so from there on in, it can actually update those registers that all the subsequent packets will actually just be expressed through the system. And so it doesn't have to go in a RAM and be chugged on by the CPU for every packet. And so the first one is required to go through that process just so that the router can figure it out. And then, yeah, it just sort of keeps that information in the cache so it knows how to forward the subsequent frames or packets. And so with Cisco Express forwarding, it's the fastest, most recent and preferred packet forwarding mechanism called Ceph. And so it builds a forwarding information base and an adjacency table. Table entries are not packet triggered like fast switching, but change triggered when something changes in the topology. When a network is converged, the FIB and adjacency tables contain all the information a router would have to consider when forwarding a packet. The FIB contains pre-computed reverse lookups, next hop information for routes, including the interface and layer 2 information. Okay, so how do we connect to a network? And so basically your home office's devices might connect as follows. Laptops and tablets may connect wirelessly to the home router. A network printer consists of connects maybe using an Ethernet cable to a switch port. The home router connects to the internet service provider by a cable modem or DSL or whatever it might be. And so, of course, a cable modem connects to the ISP network. So a branch site devices might connect as follows. Desktop PCs, VoIP phones, and corporate resources such as file servers and printers connect to a layer 2 switch. Laptops and smartphones might connect wirelessly. The wireless access points connect to switches using Ethernet cables. Layer 2 switches connect to an Ethernet interface on the edge router using Ethernet cables. And the edge router connects to a WAN service provider with whatever that is required. Central site devices might connect as follows. The desktop PCs and VoIP phones, cables again. Layer 2 switches connect redundantly to a multi-layer layer 3 switch. Layer 3 multi-layer switches connect to an edge router using Ethernet. Corporate website server connects to the edge router interface. And the edge router connects to the WAN service provider and also to an ISP for backup purposes. So that's for the bigger office. Okay. So default gateways, devices need the following information to be able to talk on an IP network. So an IP address, its subnet mask, and the default gateway. When a host sends a packet to a device that is on the same IP network, the packet is forwarded out the host interface to the destination device. The router does not need to get involved. When a host sends a packet to a device on a different IP network, the packet is forwarded to the default gateway because the host device cannot communicate with devices on other networks. So the default gateway is the device that routes traffic from a local network to devices on remote networks, such as devices on the internet. And so all of these hosts would have this interface on the router as their default gateway. And if you look at the addressing, they are all members of the same subnet, 192.168.1. This one here is a completely different router subnet because it's on a completely different site. Okay, documenting and networking addressing. So basically, when you design a network addressing scheme, don't just leave it in your head. You should document it. And so you should identify what devices, using which interfaces and what IP addresses and subnet masks they use, as well as their default gateways. And so this is an example. And so router 1, using this interface, has this IP address with that mask. Default gateway doesn't have one because it's a router, and so on and so on. So routers, of course, will have multiple IP address entries because they have multiple interfaces, while the host only has one interface. You don't really need to specify it. That's its IP address, that's its mask, that's its gateway, which happens to be that one. So PC1 connects to R1 as per the diagram. And so you need to basically document all that information. And so that's handy later if you've left the company and someone else needs to find problems. If they can find that documentation, they can then figure things out that bit easier. Now, how do we get a host to talk to IP? Now, there's two major ways. One is statically, so that's where you have to type the IP address into the device. And as long as you don't make any mistakes, it works great. But if you've got hundreds of devices, that's when more mistakes are likely. And, well, who really needs to do that? And so dynamically is where you actually have a DHCP server. The host, when it boots up, sends out a DHCP discover message saying, hey, is there a DHCP server out there? I'd like an address, please. And so from there, they get the address and they work nicely. And there's much less chance of duplicate IP addresses and all kinds of stuff like that. Okay, so probably should have been a few slides earlier, but anyway, device LEDs. Now, host computers connect to a wired network using an RJ45 Ethernet cable. Most network interface cards have one or more, two LED lights to tell you their status, basically. So green LED normally means green is good. A blinking green one probably means that there's traffic moving at the moment. No light probably means there's no cable plugged in, or it's a bad cable, or it's been turned off. So network infrastructure devices also use LEDs, and so on a catalyst switch, the green LED indicates the switch is functioning normally. Amber means it's indicates a malfunction. Cisco routers also use various LED indicators as well, and this, of course, is a indicator. And so basically, L means link, S means speed, and so green is good, off is not good. With the speed, basically, if it blinks once, it's running at 10 megabit. Twice, it's 100. 3 times, it's gigabit. So the console, basically, green is good, off is nothing, and pretty much the same with USB as well. So what ports and cables would we use? Now, to hook a console cable into a router, you would normally use the console port there with the RJ45 end, and then you would plug it into that 9-pin serial port on the computer. Of course, some computers do not have those, and so legacy free. And so another option is a USB port with a special cable into the USB console port. Now you need to load a specialized driver to actually get that to work on the computer. And away you roll. And then, of course, you need software. Now there's Terraterm or PuTTY. They're the free options available. Hyperterminal used to be very popular as well, but it's actually not available for free anymore. So yeah, basically that's how you do your initial configuration, is through some kind of console connection. So either the console cable here or USB cable. You can also do a USB to RS-232 adapter, which then plugs into that cable, and away you roll. Again, you'll need a driver for that. So IP on a switch. Switches don't actually need to have an IP address. But, of course, if you wish to reconfigure that switch, you don't necessarily want to go into the whatever room it might be in to configure it then. So some remote access so you can actually do it remotely is a good idea. And so to configure it, interface VLAN 1, give it an IP address, turn it on, tell it who its gateway is. That's all you need to do. And that will actually configure a switch virtual interface, and you'll be able to connect to the switch from there, as long as it's all correct. Now, routers and switches, the same actually. Enable secret will, of course, be that encrypted password, encrypted, well, hashed with MD5. So that's basically so you can get into privileged exec mode. You can also set a console password. And so we've done Cisco here. Then, of course, you need to sell it to use the password to log in. Line VTY, again, you can set a password and it needs to be told it needs to log in. And then, of course, these are plain text passwords by default. But if you do service password encryption, it will actually hash them. And then if someone's looking over your shoulder when you do a show run, they won't be able to see what the password is. Another thing you can do, of course, is do the banner MOTD, which is banner message of the day. And you should have something like authorized access only or something like that, just so that people know that they're entering a system that, you know, we care about. Okay. Now, configuring IPv4 on a router interface is done on the physical interfaces. So you do it on a switch virtual interface on a switch, but on a router, we do it on the physical interface. And so in this case, gigabit Ethernet 00, put in the description, which is always a good idea. And then you put in the IP address, turn it on, and away you roll. That's all you need to do per interface. And so, again, this is probably a 1941. So it's got gigabit Ethernet interfaces. You should always do show IP interface brief or something like that, and it will tell you what interfaces are on that particular router. IPv6, much the same process as IPv4, but of course you do an IPv6 address. And away you roll. Was that? Now this clock rate command, because it's a serial interface, you need to do that on the DTE end. But on packet tracer, it's actually done automatically, so it's not a big challenge. You can also, of course, do link local addresses. It talks about it here, but it doesn't show it. And so, you know, the FE80 address, you can make that a little simpler. Loopback interface. Different uses for different things. You might want to use it for OSPF. You might actually use it with BGP as well and things like that. So basically, it's a virtual interface as opposed to a physical one. The advantage of that is it's always going to be up if the router's up. It's not depending on a cable working. And so that gives it some reliability, and OSPF does like having an interface like that to use for certain things. And BGP can use that as well, as I said. So as I said, show IP interface brief is a good way to see what interfaces are on the machine, and also gives you their status. So protocol up and physical interface up. So that's as good as you're going to get when it comes to that. Show IPv6 route, of course, is the IPv6 routing table. And so you've got the source information, the destination network, and how to get it there. These are all directly connected, so it's not a challenge. When you do show commands, you can actually filter it. So begin at gateway, or show IP address, show IP route, begin gateway. So it just chops out all that explanatory information. Show running config, you can just do section or start or begin and things like that. But I don't think it's supported in packet tracer, so yeah. Command history, of course, you can use the up arrow key or Control P for previous. And so it will show you by default the last 10 commands. You can actually change the terminal history size to be bigger or smaller. In this case, 200 as opposed to 10, which is nice. Okay, so how does a router make forwarding decisions? And so basically the primary function of the router is to forward packets toward their destination. It uses a switching function, which is a process that accepts a packet on one interface, forwards it to another interface, and so that's the decision process. Then of course the switching is actually where it gets the physical moving from port to port. The switching function also encapsulates the packets in the appropriate data link frame type for the outgoing interface. And so as you can see, this is the sending host, I'm assuming. So of course it goes down all 7 layers. Once it's reached layer 1, it goes across the piece of cable. Then it's received at the router because it's a remote host. The router only needs to look at layer 3 information to make a forwarding decision. Doesn't worry about the top 4 layers. If it knows how to forward it, it then goes down, gets encapsulated, and so on. So that layer 3, as I said, is the layer that goes all the way through. This is from last term. Layer 2 is changed at each step along the way. So when a router receives a packet from one network that is destined for another, the router performs the following 3 steps. It decapsulates the layer 2 frame header and the trailer and exposes a layer 3 packet. It examines the destination IP address to find the best path. If the router finds a path to that destination, it encapsulates the layer 3 packet into a new layer 2 frame and forwards it out the exit interface. As a packet travels from source device to destination device, the layer 3 IP addresses do not change. However, the layer 2 data link addresses will change at every hop. So, for PC1 to send a packet to PC2, so across several router hops, it must determine if the destination IP address is on the same network as it. Of course, it isn't. The PC1 will obtain the MAC address from its ARP cache or use an ARP request. Because it's on a different network, it forwards it to the default gateway, so it may need to send an ARP request about the gateway's IP address. To determine the MAC address of the default gateway, checks its ARP table, or it will send out an ARP request, as I said. When PC1 has the MAC address of router 1, it can then forward the packet. When router 1 receives the Ethernet frame from PC1, it examines the destination MAC address and sees that it's the address for it. And then, of course, it's got a type field that tells it it's an IP packet, and so R1 decapsulates the Ethernet frame. Because the destination IPv4 address is not any of its IP addresses, it will then make a forwarding decision. And so it will look up the routing table. In this case, it's looking for this network here. And so it finds out the next hop is 192.168.2.2. And so it will then, of course, need to know the MAC address of the next hop. Probably in its ARP table. I'm assuming they talk to each other fairly regularly. And so then, because the exit interface is on an Ethernet network, R1 must resolve the next hop. When the R1 has the MAC address, it can then forward the frame out of fast Ethernet 01. Okay, so then it will arrive at packet router 2, and basically the same process, except the outgoing interface is not an Ethernet, it's a serial. So it'll either be triple P or HDLC, depending on what's configured. Because there are no MAC addresses on serial interfaces, R2 sets the data link destination address to equivalent of a broadcast. Because on a point-to-point, there's only 2 hosts, itself and the other one. So it arrives at R3 from that serial interface, triple P. And so it decapsulates a triple P frame, searches in the routing table for the destination. Oh, that's a directly connected network. So now it needs to know the MAC address of PC2. So it may or may not need to send an ARP request. And then, of course, it will forward it to PC2. It's gotten to its destination. Okay, so routing decisions. The primary function of a router is to determine the best path to send packets. The routing table search results in one of 3 path determinations. You've got a directly connected network. So basically, so it's learned it when it booted because it's directly connected to it. You've got a remote network, and so that's either from a static route or a dynamic route learnt from another routing protocol. And so it will forward it to the next hop router along the path. Or if it doesn't know how to find the destination, it will either send it the gateway of last resort. So basically, if in doubt, send it to there. So in this case, it could be your ISP or whoever it might be. Or if there's no gateway of last resort, it will dump it. Now, determining the best path to a destination network involves the evaluation of multiple paths and selecting the optimum and shortest path to reach the network. The best path is selected based on a metric or value that is used by the routing protocol. The best path to a network is the path with the lowest metric. A metric is a value that is used to measure the distance to a given network. Each dynamic routing protocol has their own rules and metrics to build and update routing tables. For example, RIP uses hop count, OSPF uses cost, which is calculated from bandwidth, and there's EIGRP, which uses bandwidth and delay, and possibly load and reliability. We'll talk about EIGRP in Cisco 3 if you continue on. Okay, load balancing is if a router has two or more paths with identical metrics to the same destination, the router will forward the packets using both paths. The routing table contains a single destination network that has multiple exit interfaces. It will do equal cost load balancing. So in other words, it will send the first packet on the first path, the second packet on the second, then the third on the first, and the fourth on the second, and so on. Now, some routing protocols like EIGRP support unequal cost load balancing, and so the number of packets sent are proportional to the desirability of the path, basically. Now, there's different ways you can learn destination networks, and so you need to have some way of having a tiebreaker. And so basically, it's called administrative distance. And so if you have a directly connected network, that is extremely reliable. So if you're directly connected to a network, that's pretty damn reliable information. And so the lower the admin distance, the better. And so while routing protocols are basically routed as being the most reliable to the least reliable, that's what they're saying. Now, I don't necessarily agree with all their ratings, but anyway, but that's how it works. And so basically, how much do you trust the route? You can change the admin distance as well, if you're feeling that way inclined. And then there's router operation. And so, of course, a major part of that is the routing table. So, of course, you get directly connected routes. And so when an interface is up and it's got an IP address, it will be in the routing table. And then remote routes are either learned by statically configuring them or by being learned by a dynamic routing protocol. A routing table is a data file in RAM that is used to store information about directly connected and remote networks. The routing table contains next hop associations for remote networks. Association tells the router what the next hop is for that particular destination network. So the sources available, basically, if you do a show IP route, it will actually, and I don't know why they're showing us a show running config, but anyway, if you look at a routing table, these are some of the more common ones you'll see. So local basically means a local interface. And so that will actually give you the IP address of a local interface. C means it's a directly connected network. S means this router's been learnt statically. D means it's been learned from EIGRP. And O means it's been learnt from OSPF. So here is an example of a routing table entry. So D means it's been learnt from EIGRP. This is the destination network. So 10.110/24. So here is that admin distance we were talking about. So EIGRP's admin distance is 90. This is the metric. So how far away is that destination network? So 10.110. This is from router 1, and so 10.110 is over here. So that's the distance. So that is the next hop interface. This is how long since I've heard from that neighboring router. So 5 seconds, that's not long. And this is the exit interface for that, that route. So here we've got an empty routing table. So basically, this router hasn't been configured very enough, I don't think, because it should have 3 entries at the very minimum for the 3 directly connected networks. So either the cables aren't plugged in or the information hasn't been put in yet. So a new router without any configured interface will have an empty routing table as shown. Before the interface state is considered up and up, the interface must be assigned a valid IPv4 or IPv6 address, must be activated with the no shutdown command, and should have a carrier signal from neighboring devices. So, to know that the status of the cable is up. When interface is up, the network of that interface is added to the routing table as a directly connected route. And so a directly connected route, especially with iOS version 15, you get 2 entries. One is the directly connected network, and one is the local link. And so as you can see, the local link is /32, which means this is the host address, while this is the network number, /24. And so directly connected, and that's the physical interface. So you don't get as much information because you don't need it. And so here you can see you got your C and your L entries for the 3 interfaces that are directly connected. And so as you learnt last time, router interfaces by default are turned off. And so if you want to turn it on, you actually have to do no shutdown. Shutdown turns it off, no shutdown turns it on. Now in IPv6, again, very similar, but of course the addressing is different. You still get your C and L entries, and it's not showing as a table, bugger. Now, static and default routes. So after directly connected interface is configured and added to the routing table, then static or dynamic routing can be configured. Static routes are manually configured and define an explicit path between 2 networking devices. If the network topology changes, static routes must be manually reconfigured. So what's the advantage of static routes? Improved security and resource efficiency, because routing protocols send information across the networks. So that means it gives you a chance to be intercepted. And of course, resource efficiency, you don't need to send that information. And so you don't need a routing protocol using RAM and bandwidth and all that as well. But it's not dynamic. So there are 2 main types of static routes, static and default static. So a static route is to one particular destination, while a default route is, if in doubt, use this route. So of course the command is IP route, then it's a destination network, it's mask, and then you can either use next hop IP address or exit interface. Now, next hop IP address will always work. The exit interface will not always work, especially if it's a multi-access network. So a default route is basically the same, except the destination network is all zeros and the mask is all zeros. And then you use an exit interface or next hop. And so basically this default gateway is, if I don't have a better route, I'll use this one. And so here's an example, IP route, quad 0, serial 000. So that's how you enter a default route, exit interface of serial 000. And so now you can see in the routing table that there's this static entry, destination of quad 0, and that's the exit interface. Now with IPv4, you also get a line saying gateway of last resort is quad 0. And so that 2 indications that you got a default route. That star means it's a candidate to be a default route. Of course, this is a static route, IP route 192.168.10.0. And it's 24-bit mask, and then either an exit interface or a next hop IP address. So IPv6, again, is not greatly different. Now, when can you say an IPv6 address is shorter? when it's a default route. So IPv6 route, 2 colons, of course, means 128 zeros. /0, that's the subnet, that's the prefix. And so then S000. So that's actually achieved the same as that quad 0 IPv4 route. Of course, this is a static route. And so again, this is the destination network, next hop IP address, or exit interface. Now, dynamic routing, we will go into in a later chapter. So basically, the routing protocols are used for routers to share information about the reachability and status of remote networks. Rather than manually configuring static routes, dynamic routing protocols use network discovery to share information about the networks that it knows about with other routers that are using the same routing protocol. Routers automatically learn about remote networks from the other routers. These networks and the best path to each are added to the routing table of the router. Routers have converged after they finished exchanging, updating the routing tables, and the routers then maintain the networks in their routing tables. So, IPv4 routing protocols, one of the major advantages of dynamic over static is they can determine a new best path if the primary one fails. Dynamic routing protocols can adjust to topology changes without involving a network administrator. And so the ones that are still in use these days, EIGRP, which is Cisco proprietary, OSPF, which is standards-based, ISS is also standards-based, and RIP is standards-based, but a bit old. Now, if you do router question mark, it'll actually tell you what ones are supported. Okay, so we've looked at how to configure a router to route between multiple directly connected networks. We've looked at how routers use information and data packets to make forwarding decisions in a small to medium-sized business. We've explained how a router learns about remote networks when operating in a small to medium-sized business network. There's the logo. So, of course, Chapter 2 was also for this week, and so that video will follow. Have a nice day.